Alright, silly people, here's the situation. We're going to be proving that for a couple of different Hermitian operators that the textbooks has already talked about, that a couple of things are true. That all of the eigenvalues are real, and that all of the eigenfunctions that have distinct eigenvalues are orthogonal. Um, Now, because these are both eigenfunctions, or I mean operators that have been talked about in examples and in problems in the past, we already know what the eigenvalues are for both of these, and also the eigenfunctions. For the first one, this guy, the eigenfunctions are all a e to the minus I q phi, where a is a normalization constant that depends on which eigenvalue you have. And then the eigenvalues are just the entire set of integers. So it could be 0, it could be plus or minus 1, it could be plus or minus 2, yada, yada, yada. So yes, the eigenvalues are real. So that's awesome. But we also need to check if the eigenfunctions for distinct eigenvalues are orthogonal. In other words, if you have this eigenfunction f with q equal to n, inner product that with the eigenfunction with q equal to m, where m is not equal to n, is this equal to 0? So we're going to check that. So I'm also going to use a different label for the normalization constant for each one, since the normalization constant, again, it depends on the eigenvalue that you use. So on the left here, I'm going to have just a, and then it's the complex conjugate of the eigenfunction here, so it's going to be e to the plus I n phi. Inner product that with b is what I'm going to call that normalization constant, e to the minus I m phi, and check that this is in fact 0. So now moving to integral notation, that's the integral from 0 to 2 pi of d phi e to the I n phi e to the minus I m phi, which you combine the exponents together to give you I phi times n minus m, and then just do the integral that shows up. So you can get an ab over I n minus m, but then we have to evaluate e to the I phi n minus m at the endpoints. So that's going to be, this guy is 2 pi I times n minus m, and then this, if you plug in 0 for phi, you're just going to get 1 in your exponent. But since n and m are both integers, it's safe to say that n minus m is also an integer, and e to the 2 pi I times an integer is also always equal to 1. So this is also 1, which makes this bracket 1 minus 1. And then we don't really care about the constants on the outside. You can see that those square brackets gives you 0. So this is true, at least for this eigenfunction and Hermitian operator and stuff. And the point of this problem is to show you that this is true for any Hermitian operator, because like a second before in the page opposite this problem, it says that these theorems are true for any Hermitian operator. We're just hard testing that. The next one that we're going to do is the guy from a different problem, d squared d phi squared. Don't watch my video on this, I look really bad in it. But the eigenvalues for this are just the set containing all minus n squared, such that n is an integer. So it basically, like, all the eigenvalues are either are just negative perfect squares. So it could be 0, or perhaps -1, or perhaps -4, or perhaps -9, dot, dot, dot. And the eigenfunctions for this operator as well are a e to the plus or minus root q phi, where the plus or minus means that if you pick a eigenvalue, say -1 or -4, there actually are two eigenfunctions that correspond to that eigenvalue because this spectrum is degenerate. But that's fine. For this problem, we're just going to keep the plus or minuses throughout the work here, and show that it still gives you 0 whenever we keep it, even though we really don't need to. So we're checking f where q equals -n squared is orthogonal to f with q equals -m squared, where n and m are not equal again. So, okay. So here we've got a e to the plus or minus the square root of -n squared phi, and we have to conjugate that. And then here we've got b e to the plus or minus root, just -m squared in here now, times phi. So I'll do it in, or I'll pull the a and b out because we don't care about those anymore. And then do the square roots. So this is plus or minus I n phi, which we have to conjugate, and then e to the plus or minus I m phi here. So for that, I'll write it in integral notation now. It's the integral from 0 to 2 pi d phi of e to the plus or minus, or when we do the conjugation, it's going to end up being minus or plus I n phi times e to the plus or minus I m phi. Right. And I'm going to make that minus or plus look better. And just like before, we're going to combine the exponentials to have e to the minus or plus I phi times n minus m, and then do the integral so we can pull out a minus or plus ab over n minus m, and then inside the stuff we have to evaluate, we've got e to the minus or plus I phi n minus m. And then plug in the endpoints. So we got e to the minus or plus 2 pi times n minus m minus 1. And again, whenever you have e to the I 2 pi times something, an integer, then you get 1, and n minus m is still an integer. So this is still 1. This is being subtracted by 1. So it is, in fact, still equal to 0. And I don't think I pointed out, but yes, negative integers are, in fact, real. So both of these Hermitian operators pass the test of this proof. All right.